The Earth is about 4.6 billion years old. Scientists accept the solar nebula theory to explain the formation of the Earth and the solar system. Before the Earth, the Sun, or the solar system formed, a massive star exploded in a supernova, creating a nebula, or cloud of gases and dust in space. Because this cloud was the remnant of a massive star, it was enriched with some heavier elements such as iron, gold, lead. About 5 billion years ago, this nebula began shrinking under the pull of gravity. As it shrank, it rotated or spun faster and faster. Material towards the center of the disk compressed due to gravity and grew hotter and hotter until nuclear fusion began, creating a new star, our Sun. Around the Sun swirled a disk of material which grew white-hot from the compressive forces. This disk of leftover material, called a protoplanetary disk, eventually became the Earth and the other planets in our solar system. As the Sun began to convert hydrogen into helium through nuclear fusion, powerful streams of charged particles called the solar wind began to blow outward from the Sun. These solar winds were so powerful that they blew away most of the gaseous part of the protoplanetary disk, leaving only the solid debris behind. As the Sun grew larger and hotter, the disk surrounding it began to cool and formed into small, dust-sized grains over millions of years. Iron, metal, and compounds of silicon, magnesium, aluminum, and oxygen cooled first. Slowly, these grains settled together and collected into clumps, then into chunks, then into boulders called planetesimals. This video was filmed on the International Space Station. In the bag are salt and sugar. In the microgravity of orbit, with the large gravitational pull of Earth nullified because of freefall, the salt and the sugar particles exert gravitational pull on each other and begin to form clumps, which attract other clumps. This is the process that formed the planets. As time went by, the planetesimals grew by collision with other objects. As their masses grew larger, so did the size of the collisions. These powerful collisions caused melting and vaporization. The chunks, boulders, and planetesimals left continued to collect into a handful of large, stable planets. After the initial formation of protoplanets, remaining gas and dust were blown away by the solar wind. The Earth formed about 4.8 to 4.5 billion years ago. For a long time, the surface of the Earth was completely molten, with no solid surface. As time passed, the Earth's interior heated up by a combination of 3 processes. Number 1. Gravitational compression. Gravitational energy is converted into heat energy as the Earth was compressed under gravity. Number 2. Meteor bombardment. Meteor bombardment heated up the planet's surface via shock waves and impact melts. Number 3. Radioactive decay. Radioactive elements in the Earth decayed and produced heat. As the temperature rose, iron began to melt. The denser elements sank towards the middle of the planet, creating the Earth's iron core. This differentiation, or separation, caused the heavy metals, iron and nickel, to concentrate in the core of the Earth, where the light elements, oxygen, silicon, aluminum, concentrated in the outer layer of the Earth, called the mantle and the crust. The outer crust of the Earth began to cool, while the interior remained very hot, and still is. At that time, the Earth was probably a barren planet, pockmarked by meteor bombardment, and may have looked a lot like the surface of the Moon. The oldest surviving rocks on Earth were formed about 600 million years after the Earth formed. The oldest rocks found on Earth, dated by the uranium-lead method, are about 4 billion or 4,000 million years old. Very old rocks on Earth are difficult to find because the surface of the planet is always changing. The processes of plate tectonics creates new rocks, while weathering and erosion forces break other rocks down to dust. The surface of the Earth is dynamic and constantly changing. There are several hypotheses that explain the formation of Earth's moon. The Moon is not the largest satellite in the solar system, but it is unique because of its large size relative to the size of the Earth. The Moon is about 1/50th the size of Earth. The current accepted hypothesis is the giant impact hypothesis. During the formation of the early solar system, planetesimals were constantly bombarded by debris and colliding with one another. The Earth was struck by a planet-sized object that scientists call Theia. Theia struck the Earth with a glancing blow. This impact likely flash melted the surface of the Earth and destroyed Theia, spraying debris. This debris material eventually collected and formed into the Moon over about a year. The giant impact hypothesis explains the extremely large iron core of the Earth. The iron core of Theia melted and added to the Earth's iron core, as well as why the Earth and the Moon share many of the same types of rocks. The Moon was initially much closer to Earth, but has been drifting away from the Earth since its formation. About 4 billion years ago, Earth had very little atmosphere, more similar to the Moon than the Earth's current condition. Steam escaping from the Earth's crust and gases released by volcanoes began to form Earth's early atmosphere. These volcanic gases consisted mainly of carbon dioxide, methane, and ammonia. Volcanic activity was very intense on the Earth due to the high internal temperatures, which have decreased since. Without an ozone layer, ultraviolet light radiation flooded the surface. The atmosphere at this time contained huge amounts of carbon dioxide and very little oxygen. The Earth would not have been livable for humans or other animals at this time. Our planet is currently covered a little more than 70% by oceans, but the early Earth would have been much different. Most of the water in the oceans was imported by collisions of icy comets and ice-covered asteroids. Remember that the early solar system was a much more violent place than the modern solar system. Scientists refer to this violent period as the heavy bombardment. These icy comets and ice-covered asteroids brought tremendous amounts of water to Earth. Water vapor was also released from erupting volcanoes. This water vapor eventually cooled and condensed to form clouds and rain. Together, water vapor from volcanoes and icy comet collisions filled up the ocean basins. As rainwater ran over rocks, it caused weathering and erosion. These weathering processes broke down the rocks, releasing ions into the water. These ions are what caused the oceans to be salty. Remember that Earth's earliest atmosphere was made of mostly carbon dioxide and methane. Ultraviolet radiation from the sun broke down the ammonia and methane in the atmosphere into hydrogen, nitrogen, and carbon dioxide. By 3.4 billion years ago, nitrogen had become a major part of the Earth's atmosphere. By around 3 billion years ago, modern photosynthesis had evolved. This type of photosynthesis used the abundant carbon dioxide in the atmosphere and water as raw materials. With the energy from sunlight, these early single-celled blue-green algae, also known as cyanobacteria, produced oxygen through photosynthesis. Each cell of algae only produced a tiny amount of oxygen, but the combined efforts of many cells over a vast time created huge quantities of oxygen. Remember that trees, flowers, and other green plants were not yet around. This early photosynthesis was all single-celled algae and bacteria. Over about 200 million years, the oxygen the algae produced began to accumulate or collect in the atmosphere. Eventually, the levels of oxygen rose so high that it began to poison the algae and bacteria that produced it, forcing the evolution of new bacteria that used oxygen in respiration. This occurred about 2.4 billion years ago. It took nearly 1.5 billion years to produce enough oxygen to create free oxygen in the atmosphere. Free oxygen is oxygen that is not bound up with another element, such as carbon dioxide or sulfur dioxide. Some of the free oxygen was changed by ultraviolet radiation into ozone, or O3, which collected in a layer near the upper part of the atmosphere. The ozone layer absorbs ultraviolet light that passes through the atmosphere. Without the ozone layer, ultraviolet radiation hitting the surface would have caused high levels of mutation in cells. The excess oxygen may have also reacted with methane in the atmosphere and helped trigger the largest glaciation event in Earth's history that led to a snowball Earth where the entire Earth from pole to equator was covered with ice, and this event lasted about 300 million years. Currently, our atmosphere is about 78% nitrogen, 21% oxygen, and 1% other gases, including mainly argon and carbon dioxide.